This is video 2 of Module 5. In this video, we're going to define a hierarchical network. We're going to look at some examples of such a network, and we're going to find the clustering coefficient of these hierarchical networks. So, an intuitive definition of these networks is layered graphs, or you can think of having copies of small graphs that are highly connected to each other in a layered or structural way. The example that we're going to construct is we will begin with a small network and we'll create many copies of that one network. So, for example, let's start with a triangle, or a C3. Now that we have our C3, we want to make many copies of the C3. Now that we have copies of the C3, we want to connect these copies to the original C3 by some specified procedure. Let's define our procedure to be choosing 2 of the nodes in the triangle below and connect each of those 2 nodes to 2 nodes in the original copy. Now I've only illustrated it here for the first and the last, but assume that we're going to do this for every triangle in every copy. So if we only make 3 copies, then we can more easily illustrate what it would look like when we connect each of the copies to the original graph. In some sense, what we're defining here is a type of star graph. We can think of the original graph or the original network in the same way that we can think of the central node of a star. And then each of the copies are the nodes on the periphery. In that sense, we can think of nesting in each node of the star graph another graph. Let's look at another example. In this case, we start with a small graph, so we'll start with the C3 again. But instead of making copies of the C3, let's make copies of a K2. Let's just make copies of an edge. Now, the procedure for connecting these copies of a K2 to the original C3 is to join every node in the K2 to every node in the original C3. So, what is the clustering coefficient of this network? Well, there are 2 types of nodes. There are the nodes that are in the triangle, and the nodes in the triangle are of degree 8, and there are 3 of those. And then the nodes in the edges below, and they're each of degree 4. So there are 6 of degree 4. So let's start with the 6 nodes of degree 4. I claim that they each have clustering coefficient 1. Because if you look at a node below, then that node together with its neighborhood is a complete graph, because we've connected every node in the edge to every node in the C3. So each of the 6 nodes, 2, 4, 6 across the bottom, they each have clustering coefficient 1. Now, what about one of the nodes in the triangle? Their neighborhood is size 8. They're adjacent to everything, so their neighborhood is actually the entire graph. And so the maximum number of edges in their neighborhood would be A choose 2. But if you count, there are only 16 induced edges, because there are no edges running between the copies of the K2 block. So this ratio of 16 over A choose 2 reduces down to 4/7, fairly close to 1/2. Now, what is the average? Since there are 6 nodes with clustering coefficient 1, and there are 3 nodes with clustering coefficient 4/7, we'll find that sum and divide by 9, because there are 9 nodes all total. And so this expression reduces to 6/7, so the average is relatively high. And that's because all of the nodes on the periphery had clustering coefficient 1. So we've talked about what a hierarchical network is. We've looked at some examples of these networks. We have found the clustering coefficient again. And we've discovered, at least for our example, that the clustering coefficient was fairly close to 1. So this appears to be perhaps another way to construct a small world network. More on that later.